Colour doesn't exist. What do I mean by this? Well, the first thing we have to do is to define what colour is. The electromagnetic spectrum is the entire range and scope of frequencies of electromagnetic radiation. It covers everything from the very low frequencies used for modern radio communication at one end to gamma radiation at the high frequency end, covering wavelengths from thousands of kilometres down to a fraction of the size of an atom. Somewhere roughly in the middle of this is the visible spectrum, that part of the spectrum that the two receptors above our noses have evolved to detect. It's the part that the sun emits most of, hence why it makes sense for us to have evolved to detect it. Our eyes contain rods and cones. The rods detect light and shade, and the cones detect colour. There are three types of cones, each detecting a different part of the spectrum: red, green and blue. When the light from the sun bounces off a red apple, the apple absorbs the green and blue parts of the visible spectrum and reflects the red part. This light is then detected by the cones in the back of our eyes, and we see the apple as red. So nothing has colour. Objects simply reflect different wavelengths of this small part of the electromagnetic spectrum. Colour has evolved as a survival mechanism for us and other members of the animal kingdom, and our eyes are an amazing product of evolution. We can detect approximately 10 million colours. And it's no surprise that computers are also set up to use red, green and blue. If you look closely at the individual pixels on a computer screen, you'll see that each is made up of different intensities of red, green and blue. Where the intensity of all three is 0, the colour is black. Where all three have full intensity, or a value of 255, the colour is white. And any other colour can be made up by using varying intensities of red, green and blue. And because there are 256 values of each colour, it means that the total number of colours that your computer screen can show is 256 times 256 times 256. That's a total of 16,777,216 colours, more than your eye can detect. Do you want to see all of the 16 million plus colours on screen at the same time? I thought you would. There are 256 squares in this image, and each one is made up of 256 by 256 pixels. So now you're looking at every colour it's possible to show on a computer screen. So we know there are three primary colours, red, green and blue. But there are also three secondary colours, cyan, magenta and yellow. The three secondary colours are the opposite of the three primary colours. Try this experiment. Stare at this green screen for 10 seconds. I'm now going to show you a grey screen. Ready? 3, 2, 1. Did you see a pink flash when you first looked at that grey screen? This is because photochemical activity in the retina continues even when you are no longer experiencing the original stimulus. The pink was in fact magenta, which is the opposite of green in the colour wheel. If that didn't float your boat, try this one. Here is a monochrome image. I'm going to show this to you again in a few seconds, but first, take a look at this image. Stare at the dot in the centre of the image and keep staring at it for 20 seconds. Keep staring, and I'm now going to show you the monochrome image again. Ready? Keep staring. 3, 2, 1. Wow, can you see that? Your eyes are seeing a coloured image, but now those colours are fading. The image you were looking at was never in colour, but the after image effect told your brain something different. Colour perception can also fool our brain. Take a look at this Rubik's Cube. The brown square on top and the yellow square on the front side look very different. But look what happens when we link them together. They're the same colour. And guess what? The two yellow circles on this board are also the same colour. But what about the grey squares that the two yellow circles are sitting on? They're very different, aren't they? Let's join them together and see. Did you expect that? Finally, here's a quick game. Read aloud the colour of these words as they appear on the screen. Ready? Okay, here goes. How did you do? Quite tricky, isn't it? Want to try again? Okay, here goes. Did you know colour could be so interesting?